Okay, so basically we're ready to start now for the next talk, which is called Rootkits as Reversing Tools. And you might be wondering why there's no one at the stage except for me. I'm just the herald, I'm not the speaker. This is because this is a first at the Congress. It's going to be an anonymous talk given via voice over IP via Tor and virtual network computing via Tor. So I hope everything is set up completely now, and enjoy the show.
Okay, so this is ELF 2342, also known as the Space Pope, channeling through Alan Bradley, and routing through the Tor network to talk to you about rootkits as reverse engineering tools, featuring Tron. But first we should probably talk a bit as to why no one's before you at the podium. So this is a proof of concept talk. The idea is to demonstrate that anonymous public speech is now a technical possibility. There may be some social difficulties involved. We'll address those in the feedback at the end, I guess. So to make this real, we're going to break the USA DMCA live and with mostly an active speech. And the hope is this sort of venue or format will be useful for those who research DRM or would like to give censored talks in various countries. It also serves as a nice demo that Tor is useful for some interesting stuff, other than just routing web pages and porn. So the DMCA does in fact exist. So let's look at, since this is probably predominantly a non-US audience, let's look at this law a little bit. The pertinent part states that no person shall manufacture any component or part of any technology that has either limited commercially significant purpose other than to circumvent copyright, or is marketed by that person for use in circumventing copyright. So it seems like C should have First Amendment issues. Maybe it doesn't. Maybe those have been obviated with commercial speech. I mean, Stan doesn't seem to enjoy any protection, for better or for worse. So, but nonetheless, this does present quite a few challenges or problems for security researchers. The first question, I guess, is do free research tools have commercially significant purposes? Maybe, maybe not. If you're giving something away for free, maybe it won't see use, maybe nobody will find it useful, maybe there are better alternatives. It is, after all, just a research tool. You're basically just experimenting. So you don't really know about point B. You don't really know if your tool has other commercially significant use, even if you think it should. So then what counts as marketing? And this seems awfully close to speech. If I just were to tell the truth, if someone were to ask me what are some of the uses of Tron, and I say, well, yeah, one of them is, in fact, can be used as a component to help circumvent some copy protection scheme somewhere. If I say that, it seems like I've run afoul of point C back there. So, I mean, anything, and this is true, Tron is a memory cloaker, for those of you who haven't seen the abstract. It can cloak modifications to program memory, so any copy protection that will rely on verifying the integrity of its code is a target for this. You can cloak your crack of this code and then ship it with Tron. Of course, this may be a little bit ridiculous to ship a kernel driver with your wares. There are probably better ways to do this, but, you know, it can be done. It is possible to use this thing in this way. I'm not going to say otherwise, because, you know, what the hell. All right. So we have a lot to cover. We have two rootkits, used primarily as reversing tools. Rootkit support lib to help these out, and an IDA plugin. And then we're going to also discuss the talk setup, how basically all this was done. So the goals for the rootkits for the tools are basically debugger hiding and code modification and instrumentation. It has applications in malware research, things like Skype that verify the integrity of their code to search for breakpoints, to prevent reverse engineering, and are active in searching for debuggers. DRM research, of course, which is illegal if not a serious gray area. And then cheating at online games. So, first we're going to discuss Tron, but by way of that we probably should do a little bit of recap of how virtual memory works. So basically you have this component of your processor, the memory management unit, and this handles translations from virtual addresses, which are the addresses in each individual program that are distinct from one another, and then these get translated by this MMU into the physical addresses, which are the actual addresses on your memory chips. So these mappings are described in these three-level data structures called page tables. So each lookup through these page tables requires 3 memory addresses to translate one virtual address to a physical address. So obviously this is quite an expensive operation. So these mappings are cached in 2 TLBs, or translation look-aside buffers. And these there's one for code, basically, and one for data. And there's also a distinction between supervisor and user TLBs. And at every context switch, the user land TLBs are flushed, so that all these mappings of all your user lands, every time you switch to a new process, those are all expired, and then the page table lookup happens and primes the TLBs each time there's a process switch. But these things are not expired at a thread switch, which makes sense. You don't want to needlessly expire your mappings, your virtual address to physical address mappings, if the virtual address is not going to change. A virtual address space. So this is a diagram from the Intel manuals of the page tables. At the top here you have a virtual address, which is broken into 3 components. The top 10 bits are used to get your offset into the page directory. This whole structure is started off by the CPU reading off its CR3 register, so it basically adds these 10 bits to the base of the page directory, gets a page table entry, uses the next 10 bits to offset into this page table to give you a physical page frame, and then the last 12 bits, 4096, are an offset into this 4 kilobyte page frame, and finally giving you that physical address that is the end result of this translation from the virtual or linear address. So that's the virtual memory recap. Let's recap Shadow Walker. So I guess first of all, when is the page fault handler called in general? In the kernel, the page fault handler is called if you have a translation look-aside buffer lookup fail, and then after this lookup fails, the page table, the processor automatically traverses the page table, and if it sees that the page table is marked as non-present, or it can't write to it, your write access bit is not set, or it can't execute on newer x86s, the execute bit is not set. And then there's one more, the supervisor bit, if that's not set. Then a page fault is triggered and the page fault handler begins executing. So the idea then of Shadow Walker is to mark pages invalid somehow. You could either do not present or you could do user supervisor distinction to cause a page fault to happen. So when this page fault handler is called, you hook it in some way. So you basically divert execution by either installing your own interrupt handler that calls the original, or putting a jump at the beginning of the original, or something like this. Then your page fault handler checks to see if this is a hook page, and if it is a hook page, the one that you're trying to hide or conceal modifications to, the page fault handler decides whether to put fake or valid data into the TLB, depending on the access type and the permissions for this. So if the instruction pointer of the fault is the faulting address, then you know that you have a code access, because the instruction pointer caused the fault. Otherwise, you have a data access. So you can prime instruction TLB, if it's a code access, with call instruction, and you can prime the data TLB with a move, basically, to read at that address after you put the proper physical address in your page table. So, not to knock the Shadow Walker work, it's really quite impressive, but it does have some limitations, and most of these they specified in their paper. So they weren't really pulling the wool over anybody's eyes. They were quite open about this. It doesn't handle writes or copy and write behavior. You basically either have to pre-touch all the pages, and you also have to put a little bit of logic to handle writes of this memory. There are races in a threaded environment. They don't really address this at all. At least a solution. They give some vague ideas but don't really provide any sort of solution. There's no user land support at all. It's primarily a rootkit technique for cloaking kernel memory. And then I think that they sort of looked at this the wrong way. I think this is probably one of the bigger flaws. I think it's sort of a hindrance to think about this as a schism between instruction TLB and data TLB, but I think it's better to think of it as what's in the page table and what's in the TLB at any given time, whether it's fake data or hidden data. If you think about things this way, then an API just sort of falls out of this thought pattern, and then code and data cloaking becomes possible, independent of one another, and you can develop all sorts of permissions based on the access point, or the accessing instruction, and so on. Ooh, we lost audio. Okay. All right. So hopefully we didn't lose too much audio there. So basically, I was just saying that code and data cloaking is possible because if you change your way of thinking about this. Also, I don't think it's so useful to hide rootkits because you can always check the page fault handler check to see if it's hooked. You can do some advanced techniques like Greg Hoglin's shadow branching is a possibility, but that can be detected as well if you're in the kernel. So Keytron features. So what does Tron do in addition to fixing those limitations that Shadow Walker does not? It allows you to null cloak memory, which is basically making your memory look unmapped. And system calls that deal with this memory are going to report that it's unmapped as well. Virtual query will tell you that it's unmapped. And kernel system calls on it will say that access denied, it's unmapped. And then also, the kernel is not trusted, so that programs can't just use their syscalls to verify their memory. Normal memory permissions are enforced to the best of our ability. And then race proofing APIs are provided to deal with the race conditions. So let's have a look at what this hidden memory looks like. So you basically have two views of a given virtual address range. You have the hidden view that contains your evil code or evil data, and your fake view that contains your normal code and normal data. And like I said, you can also have null cloak memory with it, where your evil code is in fact mapped, and when the other code tries to access this, it ends up as it shows up as not mapped. So what about permissions for this? So these mappings are well and good, but how do you govern what access what mappings? Well, you can set up regions of allowed code, which are based purely on instruction pointer only. This doesn't track your call stack or anything. Purely on instruction pointer, you can say that this region of memory is allowed to access your evil code, and then and basically anything else will get the fake view. And you can also do self-allowed memory, where the evil code is allowed to access itself, and the other code is given the unmapped view. So how the APIs work? All these APIs are basically macros that are exported in the userland header that have a non-hijack virtual alloc, which means that there's basically a 64-bit key that's given to virtual alloc, and if that key matches in kernel matches the one in user land, then the arguments are reinterpreted into the following API calls. So you have add cloak, which basically sets up your hidden memory between a start and end range, and this fake start and fake end is the fake memory that you want to hide or hide the actual memory with. And this is copied into your target PID, so you can use local stack for this or whatever, anything that's going to disappear right after the call. It's fine, it's all copied for you. And then in addition to that, all the virtual locking and copy on write probing is done for you to deal with that, so you don't have to worry about that either. Removing a cloak is pretty simple, just the range. This will also remove any associated permissions with that cloak. Then you can add allowed code between the start and end instruction pointer ranges and give that instruction pointer range access to a cloaked region. And the code regions don't need to be page aligned. The cloak regions in all cases should be page aligned. They get anded off for you and made page aligned, but things can get confusing if you don't also deal with them that way yourself, especially with sizes and such. And removing allowed removes your region, your allowed region. So core usage example. Here's probably what looks to be the most complicated diagram. You have a region of allowed code between A1 and A2 that's granted access to this evil code. You have C1 and C2 being your virtual address range that this evil code lives in, and then you also have your no map, your no cloaked memory that all other code is given access to. So this is actually accomplished with just 3 API calls. You add the cloak between C1 and C2, those are your virtual addresses, and you say that you want to map to 0, you want it null cloaked, you want it to look unmapped, and then you want to add allowed region for C1 to C2 to access C1 to C2, and that creates this arc here, the self-allowed arc. And then you also want to add allowed between A1 and A2 and grant that access to C1 and C2 as well, and that creates this arc here. And then everything else follows this arc and is presented with unwrapped memory. So to make things even easier for you, you have these convenience APIs. These basically provide you with a convenient way to injected to hide a DLL, an injected DLL in a process, and therefore get your code into a process, your hidden code into a process in one nice package. It completely closes the DLL, and it will edit the module list for you using the WinXP offsets, so that it'll disappear from like Proc Explorer's DLL lists and so on. The other 2 convenience APIs are read and write hidden out-of-process versions of basically out-of-process decloaking versions of reprocessed memory and write process memory that allow you to modify hidden memory from out-of-process or from outside, if you know the key, from outside of your allowed range. So yeah, again, these things aren't really a way to circumvent Tron, because again, there's a 64-bit key behind these that a program that you're reverse engineering is not necessarily going to know or be able to guess easily. So race proofing, I said that race conditions are addressed. So how's this done? Well, the primary race is for intra-thread scanning, when you have a scanner running on your own thread. So you have some hidden code, and then right after that's running, primes the TLBs, and then maybe then a job the scanner job gets scheduled immediately after that job, and then is able to use the TLBs, the TLB mappings to view your hidden memory. So you solve this problem by flushing the TLBs from user land and before and after your code executes. This prevents your code from being primed with fake data if the scanner runs before you, and prevents you from allowing the scanner to see hidden data if the scanner runs after you. So the other race condition issue is if you have a scanner running on a different thread. You have an inter-thread race. The way that this is done is that we actually pass the NTOS kernel swap context scheduler function. We use one of the librootkit APIs that's provided to modify this to flush the TLB on every switch, whether it's a context switch or a thread switch. So therefore, your other threads will then have to incur the page fault again and prime their TLBs before they touch that memory, just to make sure that a dedicated scanner thread isn't going to be able to grab the TLB mapping and view your hidden memory. So what are the weaknesses in Tron? Hidden code really doesn't run in VMware. I haven't tried AMD's virtualization or Intel's virtualization. That's promising, but the vanilla VMware seems to flush the instruction TLB when it does an IRET. In other words, so when the page fault handler returns from priming the instruction cache, instruction page cache, VMware flushes it and then causes you to incur the page fault again, and you basically enter into a page fault loop when you try and execute hidden code in VMware. It's really sad because it really would be ideal to be able to reverse engineer possibly malicious programs inside VMware without having to worry about them trashing your system. But unfortunately, it's not the case. But maybe virtualization technology will fix this for us. But data hiding does work though, so you can modify data and try and get results that way. So that's still a possibility. The other weakness is breakpoint verification. If the scanner sets a breakpoint, it can install an exception handler. For those of you who are familiar with Unix, there's a signal handler for sig trap, and then if it jumps to the breakpoint, it expects the sig trap or breakpoint exception to run. It has code in there to return its flow back to the proper point. And if the handler doesn't run, it exits or seg faults or something. So if you have a hidden breakpoint there, and you're trying to see if the program is trying to see if a breakpoint is, or if an area of memory is hidden or not, it can try and write a breakpoint, and if it tries to write to it, it'll write to the fake view because it won't have permissions for that, and then try and jump to it. It'll execute code in the hidden view, which won't cause the breakpoint to fire, and then it'll know that, well, this breakpoint didn't fire, control flow is not returning back to its normal path. So it's sort of the inverse of the breakpoint verification, or the debugger detection using breakpoints. So again, this only works if your data actually, or your hidden code actually presents itself as mapped. Null cloaked memory is fine because when the scanner tries to touch it or virtual query it, it's going to say it's not mapped. So there's really nothing it can do in this case. Room for improvement. In addition to weaknesses, there are just some limitations to Tron. It is not SMP safe. There's all sorts of issues with getting the page fault, installing the page fault handler on SMP CPUs. You possibly have to program the APIC to get to get this thing to work. I'm not seeing this slide change. Oh well, I'm just going to assume that it changed. So in the case of S&P, yeah, you're going to have to deal with also, in addition to locking these data structures between your CPUs, you have to install these hooks safely into the page file handler atomically. Oh. Yeah, I seem to be. So I lost some audio. Oh well. I'm also having problems with the slide. Finally, the slide changed. Okay. Okay, so room for improvement. Back from the top. Not SMP or hyperthreading safe. The SMP is a big, and hyperthreading and dual core is a big challenge because you have to install a separate page fault handler. For each CPU, and you have to do this atomically so that yours doesn't start running before the other CPUs are installed and get everything out of sync. You also have to deal with the DTLB in dual core and hyperthreading systems being shared between the two CPUs. So you have to set your process affinity and all sorts of other stuff. So that's a big hassle. Big problem. Have I completely dropped? We seem to be having some difficulties. I'll just continue. The API is not reentrant, so if you try and use Tron from multiple threads, you have to provide your own locking so that you don't end up making concurrent calls to the Tron API calls. It's not 64-bit clean. It's not going to work on 64-bit architectures. There's x86 assembly all over the place, in addition to patch guard needing to be broken. We are losing some connection quality. So optimizations that can also be done. You have to borrow. In order to speed things up, you can try and borrow a bit from the page tables to try and mark if a page is used by Tron or not, to avoid searching your hook tables or every time that there's a page fault. So you can use the proto PTE page bit or the reserve PTE bit for this. If it's not in your page tables, you should be able to safely pass that down or handle it yourself, and to prevent the OS from complaining about any sort of conflict with these bits, so long as you handle it first if it is yours. And you can also make the hook arrays into hash tables. Right now it's just a linear search on these tables. Yeah, I'm getting only intermittent connectivity here. This seems like it's a bit better. Okay. ADHD. So ADHD is a debugger detection foiler. Basically, it's another rootkit that'll try and hide the presence of a rootkit via some basic techniques. So what are these techniques for debugger detection? this is the first one is this being debugged flag in your process execution block. This is a per process userland data structure that contains this Boolean that says if there's a debugger attached or not. You can set this value from userland. It's checked via the system call or the library calls, is debugger present, and check remote debugger present. There's also NT query information process for the debug port information. Debug port is 0 if there's no debugger attached, or it's non-zero if there's a debugger attached. That's a system call. And then you can write code to the break-in function for when a breakpoint happens, or when a debugger is attached. The attaching process calls these two functions in NTDLL, and if you write your own code there, you can get it to execute and notify you that there's a debugger there. KakiWare has this little utility called anti-debug that uses this technique. You can also check your parent process ID to make sure that you weren't launched in the debugger, and you can call this system call to try and hide your thread from the debugger. This doesn't. This only prevents. This last one doesn't make your thread invisible. It just prevents you from receiving exceptions for that debugger. Going on, there's that exception checking that I mentioned earlier. You write the breakpoint instruction, and then you verify that your handler gets the exception. The same idea can be used to try and detect the closed memory in Tron. You can also check wall clock times and make sure that there's no large amounts of time passing between breakpoints. And then you can check your window titles of other windows on the system to make sure that there's no WinDebug window open or IDA window open or OllyDebug window open. And then you can check the list of running processes as well for those same things. So what does ADHD cover out of this? It covers most of them, most of the ones that were easy to do and weren't done elsewhere. It resets that userland flag just for you. You could do it yourself, but it does it automatically. And it also hooks that NT query information process and zeroes out the debug port, so it always returns zeros if there were no debugger present. And it actively monitors debug UI remote break-in and debug breakpoint for hooks. Every time there's a create thread, it verifies these functions and makes sure they haven't been modified from the originals. And we've tested it successfully defeats KakiWare's anti-debug. It also resets your parent process ID to Explorer automatically if it's not Explorer, so that's handy. And then lastly, it just completely blocks thread hide from debugger to prevent it from actually hiding the thread. So what is it missing? Well, exception redelivery, basically that writing a breakpoint issue. You can also do the same idea with dereferencing a null pointer and making sure your exception handler triggers right away. But IDA and WinDebug both have options to pass these things through, so you can get around that without ADHD. It also has, there's a big problem with spoofing get the time functions. They're not really hookable from the kernel. They're used via shared memory. So your best bet for getting around these is trying to script your timed areas of execution using a scripting language for your debugger or macros. And it also doesn't do process or title cloaking. Clue, the IDA plugin, does spoof IDA's Windows title, and you can try and use Futo, the process cloaking rootkit, to try and hide your debugger process from being noticed. So, finally, we have librootkit. I probably should have left that graphic up there for a little while longer. There's Pac-Man in the corner of that graphic. I find that amusing. We got annoyed-looking Sark over there. Okay, so what are the noteworthy librootkit APIs? Well, you have hook syscall that you can hook a system call by name. This is basically used for an OS independent method of hooking system calls without having to worry about what the slot is in the system service table from OS to OS. This is actually based on a rootkit.com post by Gareth. Was improved. The interface was improved a bit, and it actually frees the resources and the section mapping and so on. And the setup hot patch is really sweet. It basically sets up a detour style trampoline using Nicholas Capin's x86 length decoder to make arbitrary instruction modifications and function modifications to things like the scheduler, which Tron uses. There's also a pro for read and pro for write status, some other helpful things that utility functions that are in there. Borrowing memory, userland memory from the TED, a function to get the shadow table and set the interrupt vectors, and some logging functions. So hopefully that's useful to somebody. Next is Clue. So this graphic's another fun one. I like that. Wanted to put a little thing off his mouth that said, "I fear data rescue." They both threaten to expose me, and their API is broken, so I don't really have too much love for these guys. But actually, they might be here. So Clue. Clue will hook IDA's debugger functions to actually set hidden breakpoints with Tron, so that you can set hidden software breakpoints using IDA, and make these breakpoints unable to be detected by your debug process. The problem with the random system problems, the IDA 4.9 and IDA 5 debugger API is kind of insane. They have these functions that you basically install hooks for: write memory, read memory, add breakpoint, and del breakpoint. It never uses write memory to write the breakpoints, and it also randomly writes to these breakpoint memory in between the adding and deleting breakpoint calls. So it's sort of just like haphazardly writes to your memory. I don't know how you're supposed to develop like a remote debugger with this. So we had to use the Microsoft Detours library, which is sort of like the userland equivalent of our setup hot patch, to detour write process memory from IDA to hook it to see if it was writing a breakpoint to our pages, and then write the breakpoint via Tron instead. And then Clue also changes IDA's window titles to random strings to avoid detection. So that covers the window title enumeration issue. So here we have talk setup. Basically, first we made the orange anonymous, and then we went on to making a human anonymous. It doesn't really hurt quite so much, so that's okay. So components, what went into this? Well, we have the speaker laptop. This has a Ventrilo client. Talk setup. Oh, I'm gonna pause for the audio. Has the audio caught up? I show components here, so I'm going to continue. So we have the speaker laptop has a Ventrilo on it, voice changer, VNC client to connect to the desktop to handle a mouse, and of course Tor. The speaker side, on my side, has a firewall to prevent the voice changer and Ventrilo from phoning home. It seems that you could turn that off if you disable update notifications for both of them. They didn't seem to try and phone home this time, but I don't know if I fully trust them either. So the Linux, we created a Linux VMware image to basically ease setup on the audience side, So we created a Linux VM image to set up on the audience side. We used GNOME's remote desktop VNC server to give us access to the desktop remotely. Put the talk slides on there, PDF reader, and then install the Linux version of Ventrilo server and the Ventrilo client running in Wine. The various hacks we had to do to get the Ventrilo running in Wine are documented in the published paper as part of the proceedings. Last two components, of course, plenty of paranoia, possibly somewhat needlessly, but just for fun. And then also just for fun, fuck the man. Local setup. So Ventrilo has UDP traffic that you need to block. So it tries to connect to the server via UDP. That's probably not so much an issue when you're tunneling it through SSH, but just in case the IP is negotiated somehow, as is done with VoIP software often, we blocked all the traffic except for the stuff destined for our Tor router and the Tor directory servers at the firewall machine. We also set up, created a custom Tor RC to allow us to attach our own our streams to our own circuits, and then we had to tunnel VNC and Ventrilo over SSH. And then we had a nice little echo script running, so we could tell if we dropped. This echo script has been fairly continuous. So I guess there's just random buffering causing problems with backlog for voice. Hopefully, it's not been too annoying. And we haven't dropped, so that's a plus. Okay, so here's a diagram of what all this looks like. So you've got the firewall over here going over 802.11. This is optional 802, public 802.11 is available or whatever. It's not so much of a concern hiding this endpoint unless you're really worried about a global adversary or a large number of Tor nodes being surveilled. As you can see, there's only really one Tor circuit needed. We were able to multiplex VNC and Ventrilo over the same SSH connection, forwarding those ports over Tor through the internets, and then onto the display computer, the display computer's VMware image. The fake flows down here, that's an option if you want to try and create a larger confusion set, if you're worried about some data retention or a global adversary, if you're speaking about highly sensitive material where someone may actually use echelon to try and watch you or what have you. The other option is you can try and run a Tor server from your speaker location. This will keep connections alive to nodes for a long amount of time. As I discussed in the paper, really the vulnerability point from here is you have a circuit that's going to be very long, have not that much data flowing through it, and have a sort of a signature pattern, bursts of this voice traffic going through, and then a little bit of data for slide changes and mouse events. And this also happens to be going on for the exact time duration that the talk is going on. So if someone does, you no longer need to capture both Tor nodes in order to notice with a fair degree of certainty that you have the right circuit. You only really need the first one, and you only really need to surveil the first one externally. So what you can do against the adversary that's able to surveil the first Tor node externally is you can run a Tor server that's going to make long-lived TCP connections to numerous Tor nodes and keep them alive so long as circuits are flowing through those connections. And then you don't really have to worry about making a single TCP connection to a Tor node that only lasts while you're giving the talk, because your circuit will reuse an existing connection to whatever Tor node you choose. And then the Linux VM that we use to do this is redistributable. If anyone wants to seed Henry K, and I guess the 23C3 admin should have a copy of this. Maybe toss that up on the website or whatever. I don't know. Maybe it's necessary, maybe it's not. But the main problem with Linux is setting up Ventrilo and Wine. Otherwise, it's pretty straightforward. Possibly a little bit more straightforward than Windows because you don't really have to mess around with getting Cygwin and an SSH server installed on there since it's already there. So I don't know. Maybe the Linux VM is overkill. I guess that's for whoever, if anyone else, does this next. So how you build this Tor circuit? So you connect to the control port that you specified in your Tor CVET there. You tell you want to authenticate. You want to get circuit events, and then you want to build your circuit. So you say, well, extend circuit 0 to have Tor give you a number, and then you give it 3 nodes. And if you're an absolute fool, you will go through the node owned by the people who are running the conference, so that it is quite easily for them or anyone who is coercing them to trace you and track you down. I didn't do that. This is just an example. I figured I'd throw that in there because, chaos is good. So then after you build the circuit, it'll tell you when it's built. And then you can, when you make your connection, your SSH connection through PuTTY or whatever, with your proxy set, you'll get the stream event, and then you just tell it, okay, well, attach this stream that came in to circuit 27. And then it says, okay, and if it works, it tells you that, oh, it's sent connect, and then it's succeeded. If it doesn't work, maybe your exit policy is messed up, maybe the node you're using is messed up. So you might have to try again. So then beyond all that, all the just the setup, I mean, you can get owned quite easily just outside of all this elaborate networking setup. If you're, for example, releasing or you decide to include IDA on the VMware image to give a demo, all the IDA copies are tagged, and either your name will show up or a name of that's known to be on the BitTorrent servers will show up, and then you can be tracked down that way. The SDK is clean, so we don't. Thankfully, I didn't really have to worry about the plugin so much. Then for the documents involved themselves, the paper and the slides, OpenOffice was used. The open document format is XML, so it's easy to verify that there's no personal information involved buried in the docs. And then, in fact, there was a username in the form of a path. So if you're working in Windows and in Linux, and you're working like My Documents or in your home directory and desktop, whatever, your path will be in the file, even if you have told it to not save your user data. So you probably want to save that thing in temp if you actually have to distribute the originals. The PDFs probably don't have that information. I tried strings on them, and I didn't really see it in there. So I don't think the PDFs have it in there. And Microsoft does have a metadata tool to remove this from their stuff, but the document format is proprietary. If they've missed something like OpenOffice has, you can't really tell. So a pass on that. Then on the VM, even if you don't have to worry about Windows sending, doing verification against your serial number, in Fedora you probably do have to worry about the fact that the VM that all these RPMs have their install date and time. So if a motivated adversary could roll over to the Yum update servers, which do record IPs for user number tracking purposes, and say, well, this update was downloaded this time. What servers had downloaded this? What IPs had downloaded this package at this time? So you have to worry about that. The DDK is kind of a pain in the ass to obtain. It's free, but Microsoft only wants to mail it to people. And then WinDebug can give you a way when you're debugging kernel drivers and Windows programs if it tries to search the Microsoft symbol servers for your symbols. Unclear if those are logged or not. They may be. maybe not. It's probably a lot of data to log, maybe expired, but maybe not. And then, of course, Google, webmail access, and everything should be done through Tor, and the usual precautions for Tor apply. Filtering cookies and whatnot when you turn Tor on and off, and Privacy or Firefox extensions to block JavaScript and stuff. So yeah, so this doesn't hurt quite nearly as much as it looks. It's actually relatively painless, but there are some pain points. Most of all, as I is what should probably become apparent from the previous slides, is that it's easy to mess up. And then even if you do this all right, maybe it's very possible that your friends will post on forums or Slashdot to defend your talk idea, or visit the con website just to visit your abstract from their work IP or an IP that reverse resolves to their name even. Then maybe they'll mention, brag, or blog that they know the speaker. And probably even more importantly than this is the intersections from expertise issues, who has the expertise to do this. If you're doing research in a novel area that very few people do have interest in that area, you definitely have a very small anonymity set. Unless somebody came out of the blue to do this, it's possible to quickly narrow down a list of suspects from people who are known to have done rootkit work, memory cloaking work or whatever. So then from this suspect list, who purchased this equipment, tools you use, suddenly credit card purchases or whatever online purchases become a lot more relevant. Did anybody buy, IDA? Did anybody buy the voice disguiser? Did anybody buy whatever was used recently for this thing? Then mistakes during your setup. If you're doing a test, a hasty test, your firewall rules are wrong or whatever, the thing manages to phone home. Right during your test. Your voice disguiser manages to phone home. And then after this, your slide style, your speaking style, tend to say a lot. You tend to ramble a lot. So all these are sort of fingerprints that can help narrow you down. And then from here, if there's a serious motivated adversary, maybe none of this is enough to necessarily convict you, but if there's significant interest, you can, an interrogation can begin. You can start shaking down people who have said things. You can start interviewing the list of suspects, see if anybody said anything, and so on. So on top of all this, there's numerous downsides. You don't necessarily get the resume padding. The audience is deprived of the human element. I've had no feedback from you guys. Well, Mike would have been nice to see if I can hear, but there's just so many components involved. Getting them all tested and working ahead of time is just it's pretty difficult. So fortunately, we had to go without. And then it's getting it right so it's not a distraction for me is even more work. So it's pretty difficult. And then the speaker is deprived of networking with others who share interests. Well, I'll be on IRC, so that's possible there. Then if you screw up, you make mistakes, then you look stupid. And depending on your circumstances, depending on how motivated the adversary is, maybe in some trouble with the law, or angry thugs, Blizzard coming to break your kneecaps or whatever. Sony getting pissed off, Apple angry, whatever. They break knees, maybe. At least their lawyers will. So, just to catch up a little bit. Should be on Is It Worth It now. My slide still hasn't changed, but the little counter is still running, so I'm still connected. Well, maybe it's worth it. I guess you decide. Please do give feedback. We did our best. I did my best. The 23C people did our best. Some things would have been nicer, but, can't do everything right. So have mercy, but please be detailed, please be specific if you do decide to give feedback. Personal standpoint, well, I just think it's worth it for me. I thought it was really fascinating to learn about all the ways that we're tracked in a given day. I don't know. It's sort of a political standpoint just to go overkill on tracking, just because, I mean, if you look at this from the perspective of, an interstellar being from Sirius B, basically, humankind were zoo animals. The elites, or whoever has access to this data, law enforcement, private investigators, people with access to the Google logs, they can watch over us and find out what they want to sell to us, find if any of us are possible political opponents to them, what have you. It's pretty sick, if you ask me. I think it's worth it to go overkill. In trying to defeat these various tracking mechanisms, just because they're there, I guess. So then for DRM research and whistleblower info, maybe some talk is better than no talk. I think it might be useful for people who work on DRM, the people who have been broke. Oh, I've disappeared. Fuck. So I hope you got my zoo animal rant. I like that one. But so I was on to the DRM rambling. Maybe I think this might be useful for the Maxis or the people who've broken the Apple TPM protection. I think that'd be pretty interesting to see in detail a talk on that. So and it might be nice for them to be able to develop a non-corporeal persona that they can use, attend some cons, get some press for whatever aliases they decide to use. Probably better to develop a name first so that the press actually says, "Oh, this guy's talking again. Let's pay attention." So that's that. That's pretty much it, I guess. I guess if there's time, I'm about a minute early, but there should be nothing after me. There's my contact info. I'm on Freenode now until they ban all Tor users again. They've been pretty good lately, but last time I got banned out. Too lazy to do that GPG thing that they've got. Tron is at OpenRTE. That's still a TourCon version. I'm gonna try and put a 23C3 bug fix release up in a bit. Somebody reported a bug a couple of days ago with instructions executing on page fault boundaries. So I'm going to write some tests for that and investigate that. Maybe in about a week or so, I'll put a Tron version 023 up on OpenRTE. And let me know if you have notice any other bugs. Possibly going to be looking at SMP support. There's somebody else who's the same person who reported the instruction page boundary issue is also interested in working on SMP. So maybe we'll figure some stuff out together. But that's probably on the time frame of several months out. If the mic is going to work at all, I could try and take questions, I guess, or I can just hang out on IRC for a bit. I'm pretty much done. I can't hear applause. Oh, so sad. I live for applause. Or whatever. Okay, yeah, I can take questions. Hey, applause! Hooray!
Okay. So if anybody got any questions, we've got somebody who will relay it over the RIC, I guess, and well, feel free to ask them anyways over the audio channel.
I would like to thank the speaker. It's been a very interesting experience, at least for me. I think for most people here, having no speaker at front, but it's definitely nice to have it at least working and see the proof of concept running. So thank you.
I would like to know if why he didn't use something like Festival or something similar. Festival voice synthesizer.
Oh, you're welcome. Like I said, it was fun. A little stressful, but fun. Festival. Oh, actually, I did think about using Festival and going by the name 7 Hawking, but I thought that would be cute. But I think it'd be too distracting. I think I tried it for a little bit. It's hard to follow. You need intonations in voice, right? And you need pauses and stuff like that. Yeah, any text to speech has the same problems. You can't carry inflection and cadence is hard to do. It's hard to synchronize it with pointing at diagrams. Those are the main reasons, I guess.
One other question. Why not send a pre-recorded file?
Pre-record a file? Well, I mean, ideally I was hoping for some sort of mic feedback so that I could like hear, audience laughter or whatever, and respond to, if somebody wanted to shout or throw a chair or whatever. I mean, yeah, you could do a fully pre-recorded talk. I want to try and get a little bit more of the live element. I mean, both times we were unable to get the mic working, so I probably would have been better off with a pre-recorded file. But I wanted to try and get things to be a little bit more, try and keep as much of the human element as possible while doing this.
Okay, I guess if there are no more questions, we'll just wrap it up, and thanks for your time.
Okay. All right. Yep. Thanks, everyone.